Hi everyone, this is my 3D house transformation project for our course Linear Algebra. On the screen, you can see the house is composed of a yellow cube for the base and a red pyramid for the roof. The axes are color coded, X in red, C in blue, and Y in green, which is behind the house. You'll see it when we apply transformation. The origin is marked by a black dot. Also, you can see there are also coordinates displayed. The cube vertices, which means the 8 points of the cube, and the roof vertices, which means the 5 points of the pyramid. As we apply transformation, we change these coordinates. All transformations are performed around this origin. This is important because linear transformation always preserve origin, meaning it stays fixed. Except in special cases, transformation called translation breaks the origin rule. So it's not a linear transformation. So in this video, we will learn how linear transformation in 3D rotations, scaling, and reflection are represented as matrices. Let's start with rotation. Around the x-axis, by clicking the Rotate X button, the matrix displayed in the Notes panel is this matrix rotates the house in YZ plane by 15 degrees. Notice that the origin stays fixed, and the distance between points remain the same. This is because rotation matrices are orthogonal. A key property in linear algebra ensures angles and lengths are preserved. You can think of it as turning the house without stretching or skewing it. If I click Rotate X a few more times, you can see the cumulative effect, which corresponds to multiplying rotations matrices sequentially. Next, we rotate around y-axis using Rotate Y button. The matrix is now. The house rotates in x and y plane. The origin remains fixed, demonstrating that rotation is a linear transformation. Straight lines remain straight, parallelism is preserved, and the origin does not move. By combining rotation along x and y, we can achieve complex orientation, showing how matrix multiplication represents sequential linear transformation. For rotation around the z-axis, clicking Rotate Z produces this rotate the house in x and y plane. Using these three rotation matrices, we can rotate the house in any direction in 3D space while preserving the origin and linearity. Next, let's explore scaling. Clicking the Scale Plus or Scale Up button increases the house size. The matrix is scaling multiplies each coordinate by 1.2. The house grows proportionally along all axes, keeping its shape intact. Scaling demonstrates that linear transformation can change the size of objects while still preserving lines, planes, and the origin. Clicking the Scale Minus or Scale Down button shrinks down the house using all the dimension is reduced proportionally, preserving the relative proportion of vertices. Now, let's demonstrate reflection. Clicking Reflect X flip the house over the YZ plane. The matrix is X coordinates are inverted, Y and Z remain unchanged. The origin is preserved and lines remain straight. Similarly, reflecting over the y-axis flips along the XZ plane, and reflecting over the z-axis flips along the x and y planes. Reflection are also linear transformation because they preserve straight lines, planes, parallelism, and the origin. From here, we can combine transformation. For example, a rotation followed by scaling and reflection. The GUI updates the current transformation matrix, showing how sequential linear transformations correspond to the matrix multiplication. In summary, this project demonstrates how linear transformation in 3D, rotations, scaling, and reflections are represented as matrices. All transformations preserve the origins, lines, and planes. So, this is the end of the video. Hope you learned something. Bye.